Greetings once again. I'm John Gabriel and this is a new calculus channel. So I'm going to be continuing with definitions 11 through 15 of book 7 in Euclid's Elements. So let's begin. Now, definition 11 is about a prime number. What is a prime number? Okay. So Heath says a prime number is one that is measured by a unit alone. That's not actually true. A prime number is measured by the unit and itself. Okay, that's the correct thing. And Heath didn't really add that in. His translation seems fairly accurate. So it seems that the blame lies more with Euclid than with Heath in this case. Okay, so the connotation conveyed by first or Πρώτος, which is first in Greek, suggests that if numbers consist of factors, which are multiples of the unit, these would be irreducible prime factors that measure the number apart from the unit, as in the fundamental theorem of arithmetic, or the factor theorem, which is another name for the fundamental theorem of arithmetic. So reading ahead, definition 12 and 13 confirm this track of thought contextually. So it's a euphemism really to say that Heath missed quite a lot, as we shall see in our progression. Now, definition 12 says numbers are prime to one another as those measured by a unit alone as a common measure. So what this is telling you simply is this, is that, for example, the numbers 9 and 4 are prime to each other, because they're only measured by the unit and themselves, right? So 9 divides 9, the unit divides 9, 4 divides 4, and the unit divides 4. So that's what it means when we say numbers are prime to one another, okay? Definition 13. A composite number is one which is measured by some other number. Well, it's not strictly speaking correct. A composite number is a number which is measured by a number other than itself and the unit, okay? Definition 14 says that numbers are composite to one another when they are measured by a different number to either of them as a common measure. So again, there's no use of the word and in Greek, and the better way to state that definition is that numbers composite to each other, as opposed to being prime to each other, which is the previous one, are measured by a number other than themselves and the unit. And finally, definition 15. Now, we need to be very careful with this definition because it might seem that Euclid is generally defining multiplication here. He isn't. That has already been done in book 5. So all he is doing in definition 15 is defining a special kind of multiplication between special kinds of numbers, okay? Those are still numbers, but they're numbers that are multiples of the unit. In other words, what are commonly known as natural numbers. So book 5 gives a general definition to multiplication that applies to all numbers. In this particular definition, 2 multiplied by 3 means 2 groups of 3 or 3 groups of 2. But this definition is misleading because it does not actually explain the meaning of multiplication as given in book 5. So if you were to do it the correct way, as it's done in book 5, it would be a reciprocal measure of division. That is, you would need both 2 in quotientness with a third and 3 in quotientness with a half. And this is the way you would do it. You would use proposition. Can you remember which proposition? 12. Proposition 12, right? In order to find out this multiplication. And you'd have the same answer in both cases, okay? So this is the one way, and this is the other way, which must both be true. And that's why you can't really have 0 as a number, because one of these, actually both of them wouldn't work if 0 was anywhere in these numbers. So in the above, we have measured 2 with a third and 3 with a half respectively. In each case, the reciprocal measures result in 6 as required. Now, if you were to use magnitudes, this is how you would do it. You would say this here is 2, this here is a third. Okay, so 2 in ratio to a third, and now we are about to do something about the quotientness. Now, the quotientness tells us that we can add the lines, right? Okay, so we can add this 3 times to itself, and that's what we do here, and add this 3 times to itself, again through which proposition? That's right, proposition 12. Okay, and so requirement 2 tells us that we can extend or diminish line segments, so there's nothing fancy about this operation here, except that we're just extending this line segment with this much 3 times, okay? 2 times actually, to give us this, okay? And the consequent remains the same. Similarly, we're extending this part of a third 3 times to give us this, and the consequent in all these cases remains the same, okay? All these. And so we have this particular ratio here, and a proposition of Book 5 tells us that this ratio here is equivalent to this ratio. Why? Because this is proportional to this, right? And finally, we can drop this part here. We can drop this part here so that we arrive only at the ratio that describes the ratio that precedes the measure, which is 6, okay? And of course, ratio consequence, these are the ratio consequence, they're the same, so the proportional consequent of this entire ratio, in other words, this entire ratio, can be omitted, just leaving us with that. And so that's all I have for this video. In the next video, I'll continue with definition 16. This is a new calculus channel. I'm John Gabriel. Till next time, goodbye.